Hi guys. So as it turns out, I was lying about the bad mic. I have not had time to test it yet, but I will soon. So hopefully that should be up. Hopefully. We'll leave it up to optimism. So I just did this most recent round, this Div 3, round 693, and it was kind of an interesting dynamic. I had a really good time with the first 4 problems, solving them like in 7 minutes and being around third or so, and then kind of fell down from there. As you can see, had a bit of a rough time with like everything, and then spent a long time on G, and then eventually came back to get E, and then F was even more annoying. So that was a fun experience, I would say. And as promised, now I'm going to make a solutions video about the problems, so I can do that now. Let's go. So in problem A, we have essentially so we have a sheet of paper of size W times H. I think, yeah. And then we want to cut it into at least n pieces. And what we can do is, if the current paper has even width, we can split it into 2 papers of width W over 2. Also, I'm still practicing with the writing tablet. I'm probably not good enough to use it yet, so we'll leave that out for now. Or if it has even height, we can split it into 2 sides with size h over 2. And then we can treat these papers separately and divide both of these, for example, into smaller papers. And then we can do the same thing with width. So we're essentially asking, can we divide it into at least n papers? And so the idea is, when we can divide it by h, then all of the individual papers are like equivalent, and they still have the same width. So dividing it by h will basically create 2 new papers of size W and H over 2. Now both of these papers are equivalent, so we can continue splitting both of them like they're the same paper. So if we can split by H again, then we would do, for example, 4 times W and then H over 4. And we could do this splitting by height until we can't split by height anymore. That is, when it's odd. And this works because splitting by height it has no effect on whether you can split by width or not. So it's not a bad thing to split all of the heights at once. And then we can do the same thing for W until we can't split by width anymore. For example, like this. And then this gives us the maximum amount we can ever split. And then we just need to check if this number is at least n. Yeah, so basically we can just say while W is even, divide it by 2 and double the amount of papers we can have, and then do the same thing for H. So like in terms of code, this is rather simple. While the first is divisible by 2, divide it by 2, multiply our answer, and then do the same for Y, and then just check if it's greater than n. I kind of muddled the variables, so that's fine. For B, we have a bit of a different thing. Just testing to make sure. Say check. Yep, okay. For B, we have a bunch of candies, and each candy has either weight 1 or 2. And we want to ask, can we divide the candies evenly into 2 sets such that like their sets have the same sum? So for example, let's say we have 1, 1, 2. Then we would, for example, want to divide it into, put these 2 in the first set and these 2 in the second one. Call this the purple set. And then their sum is the same, so it's possible. Yeah, so It's basically like subset sum, but like a very, very special case of it. Okay, so I'm pretty sure I overcomplicated this, and there's some casework you can do. Like if you have at least 1 and it's even, you can get it, and if not, then not. But you know, whatever. This is a div 3. So what I did was I just fixed the number of 2's, so we can have either 0 to like we can keep the counts of the number of 1's and the number of 2's. And really, when we ask if we can split it into two sets of equal sum, like consider the sum of the whole set, like 1 plus 1 plus 2, and then call it S. Whoa, mouse is going a bit crazy. Then we're asking if we can create a set of size, or of sum S over 2. So we really just need to know if that's possible. You can do this via a lot of ways, like for example, you can do knapsack or something. That's a possible thing that's possible if you really want to overkill a div 3 problem. Another thing I did was I fixed the number of 2's we used. So any number of 2's from 0 to the count of 2's, and then I asked if we have enough 1's to make it to S over 2. So like for example, we use k 2's. Then the total sum we have is 2k. If 2k is greater than S over 2, then automatically we have too big of a set. So stop. Otherwise, continue. And then we need to know if we have enough 1's to make it to exactly S over 2. So then we check if C1 is greater than or equal to the distance we need to cover, which is S over 2 minus 2k. And then if this is true, then print yes. And if this is never true for any possible value of k, then there's no way to do it. Because like we're trying all the possible numbers of 2's, and if it doesn't work for any of them, then it's just never going to work. I don't know why I'm starting to go over code, but I guess why not. So basically, keep track of the counts of the variables, like keep track of the number of 1's and 2's you have, and then like if the sum is even, automatically you can't do anything. Otherwise, check all the numbers of 2's. Yeah, I'm pretty sure there's some casework you can do. Like if you have at least 1 and the sum is even, that means you have an even number of 1's. And then you can like, I don't know, I think it's just always possible if you have at least 1, and if not, if you only have 2's, then like you can have an even number of 2's or something. That would be the casework you do. I'll leave that as an exercise because I don't have it worked out. So C is a problem, and it basically asks, we have an array, and what we can do is we can pick some starting position, for example here, and then we say that we're going to have some total score. Let's say it's 0, and then what we can do is from our starting position, we can add the current array value to our score, and then we can jump the number of positions equal to the array value. So like the array value is 3, so we can jump 3 positions. And then we do the same thing here. Now we're here, and we add 3 to the score again, and then now we jump 3 further positions, and now we're at the end of the array, so we're done. And we're basically asking overall starting positions. What's the best we can do? What's the best score we can get? Now the trick is we always move forward in the array, which means that, say we've worked out the score for this one, then this jump is just going to be this array value plus whatever the score is for this. Because when we're here, we don't care where we came from, really. We only care that we're here and that we're going to keep going forward until we hit the end of the array. So if we basically iterate like backwards, then we could say, so this score is going to end up being 3, and then it's going to immediately jump off the array. And then this score is going to end up being 2 and then jump off the array. And then this score is going to be 1, and then we're going to go here. And then we've already figured out what happens when we start here, and we have this extra bonus of 1. So our score is going to be 1 plus whatever we get when we start here, which is going to be 1 plus 2, which is 3. We do the same thing here. This 3 is going to end up here, so we get 3 plus this score, which is 6. and then we go to 7, and the best answer is 7. So then going backwards, we can basically do this in O of n because every element only uses one operation, since like otherwise we'll get to something we've already computed. Like we only make one jump for each element because no matter what, either we go off the array or we get to something we've already computed to the right of it. So it only takes like one operation or so. And then the answer is just the biggest value out of all of these. So again, code-wise, it's like rather simple to do. If it will load, I would love that if it were to load at any point in time. Yeah, so I can initially set it to that, and then if the jump is still in the array, then add the sum from the position we get. That's basically it. I'll also, of course, link my submissions in the description as always so you can find them. Okay, so contest is over. I'll check my place later. And basically now, I wonder if I'll be hacked. That would be interesting, wouldn't it? Because why not, right? I've been hacked on the last Edgy round. I've failed system tests so many times. Seems like my videos are just cursed. Oh, I didn't even do a screencast this time, so who knows? Okay, this one's kind of a cool argument. So we have an array of values, and we have two players, Alice and Bob. So Alice moves first, and in one move she can take any value from the array and then cross it off so that it may never be accessed again. And basically, Alice and Bob both have their own scores. And in her move, Alice can take so if she gets an even value, it's even, right? Yeah. So if she chooses an even value, then it becomes added to her score. So like if she takes the 2, then she'll get the score of 2. And if she takes an odd value, then it's not added to her score, so it doesn't change. And so the question is, given that they can do this and then they move in alternating turns, what's the outcome of the game? Like if Alice and Bob both play optimally, what's the end of the how's the game gonna end? Who's gonna win? Or will it be a tie? And of course the winner is whoever has higher score. So now the question is like, what do you get from doing a move? And the reason this is difficult is because maybe Alice doesn't want to take the 2. Maybe she wants to take the 7, for example, to block out Bob from being able to get the 7. Right? Because that could potentially be better than getting the 2. Because while she doesn't gain 2 herself, she blocks Bob from getting 7 points later on in the future, which is better. And so the question is really, what's the benefit of taking an element? So for Alice, for example, say she takes a 2, and then we ask, like, if she does take the 2, then she would gain 2 from it. But if she doesn't take it, and ultimately Bob ends up taking it, then he would gain 0 from it. But if she takes a 7, she would gain 0 from it. But if Bob ends up taking it, then he would gain 7. And then it's kind of like the same argument for other odd numbers. Right? Because if Alice never takes an odd element, Bob is going to take it. And then that's basically how it works, because it's zero sum and they're alternating. So really we can consider Alice trying to maximize the difference between her score and Bob's score. And so if we consider elements in terms of this difference, then this is like 0 minus 5. So it's like the cost for Alice of not taking this element and leaving it to Bob is -7. Because if she doesn't take it, Bob will take it, and then he'll have an advantage of 7. But if she takes the 2, sure, she'll have an advantage of 2, but Bob would have gained 0 anyway from getting it. So it's only really an advantage of 2 for taking it. So Alice wants to make the move that minimizes, that maximizes the advantage she gets, which is the same as minimizing the disadvantage. Or Sorry, like maximizing the disadvantage that Bob gets, for example. So like in terms of this, this is the disadvantage if Bob gets it. So yeah, she wants to pick the one that's going to be the best for her. So essentially, the parity of elements doesn't actually matter. What does matter is like what the element is. Hmm. Right, okay. So if she takes the 7, then Bob will lose out on 7 in the future. So like this is the penalty applied to Bob, which she wants to make as large as possible. So really, for either player, it's always best to take the largest element, because it will either give you more points or screw over your opponent more in the future. And either way, doing either of those things has equal benefit. So Alice will want to take the thing that gives Bob like -7, and then Bob will want to take the thing that maximizes his own score, which is +5. And then Alice will want to take the thing that gives Bob -3, and then Bob will want to take the thing that the only thing left. And so Bob will end up winning this one because he gains the 5. But the point is, taking the largest element will always either give you the best score or reduce as much score as possible from your opponent. And considering that Alice, for example, is trying to maximize the difference between her score and Bob's score, both of these are equivalent, and taking the largest element will do like it'll do the most for this difference. So with that said, basically all you need to do now is iterate through the elements from largest to smallest and simulate the game. And then you can just figure out what the scores are and do that. So that's what I do. You can sort and reverse the array and then go through it, and then just figure out who gets what points. Because it's always optimal for each player to take the largest available element. Okay, next one is E. This is where the problems get more annoying, because this is the gap between me solving the first 4 in 7 minutes and then taking like an hour on this. So we have like some rectangles. So like we have a 3x4 rectangle. Actually, I should draw this. So we have a 3x4 rectangle. We have I feel like I've seen this exact problem before, honestly. A very similar problem, something very similar. So we also have a 5x4 rectangle. This is not the scale in any way, by the way, just warning you. And what is it, a 3x3 rectangle? Okay. And basically what we want to do is, so for each rectangle, we can either leave it as is or like turn it to its side so that a 5x4 rectangle will become a 4x5 rectangle. And what we want to do is, for each rectangle, we want to find another rectangle that has strictly smaller dimensions than it. So like, for example here, we would want to find a rectangle that has width less than 3, or height less than 3, and width less than 4. This accounting for the fact that you can turn rectangles. So you want to find a rectangle such that you can turn that rectangle such that it fits strictly inside this one, basically. So both dimensions are strictly smaller. That's what it is, right? Yeah. So the first step is like getting rid of the rectangle part. Actually, yeah, we want to do this for each element efficiently. We obviously can't just go through all of them. So the first step is eliminating the rectangle part. Let's see. Without loss of generality, I guess. Assume that hi is less than or equal to the width of I. Then assume we're comparing it to some other rectangle So like this height is less than or equal to this width. Then assume we're comparing it to this other rectangle whose height is less than or equal to its width. Or whose height is like greater than its width, for example. So then we have hj is greater than or equal to wj. So like, when do we want to turn it? And I guess my answer would be is that we always want to turn it. And the reason for this is like, say hi is, so we have these like conditions. So hi is less than or equal to wi, which is less than or equal to wj, which is less than or equal to hj. I'm just combining these two together. Right, so this is the necessary condition for this. And well, basically, okay. How would you prove this actually? So if like, if this isn't met, then everything, or like, no. Yeah, like if one of these comparisons isn't met, we're kind of doomed. So I feel like I'm going about this the wrong way. Okay, so yeah, okay, we can assume we're working with this inequality, and then we can say that it's still optimal to swap it, I guess. So we want that hi is strictly less, no, wait. Hi is strictly greater than hj, right? Yeah. And then also the wi is strictly greater than wj. And so the question is, will this be true even if we swap it? And if we swap it, will it be more true? Actually, we don't want this. We kind of want to swap those too. Like this is more like, so for this to be true, given that we have like this orientation, we need it to be true that like wi is greater than or equal to hi, which has to be strictly greater than hj, which has to be greater than or equal to wj. And my claim is that it's okay to swap these. And the reason is that because we know that like the height is greater already, like we have it oriented so this is true, then if this is true, then hi will still be greater than wj, because, or like this height will still be greater than this width because we have this inequality already. So therefore, making it so we don't compare these two heights, but rather we compare this height to this width is going to be okay. We're not going to change from something that's true to something that's not true. And now we were originally comparing wi and wj, but now we want to compare wi and hj. And we still have this condition. So it's fine. Actually, this is like one case. Okay, 1 second. Let me actually let me get my thoughts together. There's definitely a way to prove that it's like okay to swap these. Like we can, okay, like basically the main idea is that it's always okay to swap it so that the height is less than or equal to the width. And then we can treat it like that. And then we can sort of like ignore the rest of it. And we can ignore the rectangle part because we always have the height being less than or equal to the width. So maybe we have it like this. So we have hi is greater than hj, and we have wi is greater than wj. And we want to show that, and we also have these inequalities. And we want to show that hi is greater than wj, and wj is greater than, no, wi is greater than hj. That would show that swapping hj and wj within these inequalities is fine. So how easy is this to do? So we know hj is greater than or equal to wj, which means that we know that hi is greater than hj, which is greater than or equal to wj. So that gives us this one. And then we want to show that wi is greater than wj. And wi is greater than hi, or greater than or equal to hi, which is greater than hj. Yeah. So by like combining these two equations, we can prove this. So we can show that if we have one rectangle where the height is less than the width, and it matches with some other rectangle where the height is greater than the width, then it will also match with it when the height is less than the width. So it's never a bad thing to swap it when the height is less than the width. And sometimes it even makes it easier because maybe like the other height was too big or something, but making it smaller will then make it match with the current height. So also kind of the intuition behind this idea is that like it's going to be easier if we compare the smaller things to the smaller things rather than saying that the smallest thing has to be bigger than the biggest thing. We would rather say that it has to be bigger than the smallest thing because that's sort of easier to satisfy. And then we can compare the bigger things to the bigger things in the same way. Because if the bigger thing is less than the smaller thing, I guess, then it will also be less than the bigger thing, so that's like fine. And if the smaller thing here is greater than the bigger thing, then it will also be greater than all the other smaller things here. Okay, anyway, that's sort of my trying to explain what the intuition is. Okay, I'm gonna timestamp this part out. But so basically the idea is we can always orient the rectangles so that their height is less than or equal to their width, or their width is less than or equal to their height. Either one, but always like only one. So now we can assume for every rectangle that hi is less than or equal to wi. Which means that now we know what to compare. We know we can compare the heights individually and the weights individually, or the widths individually, and we need them both to be like satisfied. So now, basically we can sort elements by their height. And for example, say we have 3, 4, 4, 5, and 3, 3. We have 3 pairs, 3, 4. Now we have the pair 4 and 5 because we swapped the rectangle to make the smaller one first. And then we have the pair 3 and 3. So now, for the height, for like this height to be greater than this height, we can do something like sorting it. And then we need to be careful to not compare equal elements. Right. Now if we sorted them by height, then we know we can compare like this element to every element that's not equal to it. So we can, one possible way to do this is to break elements into groups by their equalness. Or you can like do a two-pointer strategy to keep track of the last index that wasn't equal. And then you can do like something else to maintain that. Like for example, this 3 can be comparable to everything before it. This 3 can also be comparable to everything before that. And then this 4 will be comparable to everything before a 4 ever happened. So now we know that H works, and now we want to find a W that works. So we're basically asking, like for example, for this 4, we're asking on this prefix of the array, is there a value of W that's less than this one? And if so, we want to find it. So that's basically equivalent to asking, is the minimum value on this prefix less than this? And then if so, where's the minimum value? Because we also need to find the pair for it for some reason. So this can be done with two pointers in many different ways. But basically what I did was I kept like prefix minimums, like the minimum of the first element, and then the minimum of the first two, and then the minimum of the first three. And while you keep these minimums, you can also maintain the index by saying like if you change the minimum, also change the index to the new one. And then with the two-pointer strategy, it's basically asking when you're here, compare it to the prefix minimum of the pointer. That is, you want to make sure you don't compare it to an equal value, which is a mistake I made, and hence some of these wrong answers. And then, yeah. So don't compare it to an equal value, and then you can just check if this prefix minimum is valid, and if so, find the index for it. So the code for this is fun, I suppose. So basically, you would find the values. I kept track of like their index and then both of their like heights and widths, and stored them as pairs. And then I sorted them by their height with this fancy comparator. And then my two pointers approach was basically saying like, so start the pointer at the beginning, or I'll stick on a new element like 4, 9 for demonstration. And then like for example, start the pointer at the beginning, and then for this 3 we have nothing to compare it with, so there's nothing we can do. It's automatically, there's no pairing. For this 3, we compare it to the previous one. And if it's equal to the previous one, then the pointer should stay the same because we don't want to include this element. So we don't move the pointer if the element is equal to the previous one. And then once we're here, we know that when we compare it to the previous one, we have a value different from it. And because it's sorted, we know that every value before then and at this one is going to be different from this one, which means that we can now move the pointer to this whole thing and then compare everything here and use this prefix. So we basically move the pointer only if we have two adjacent values that are different, and then just compare it to the prefix minimum. If it's like less, then set the value to the index and then continue maintaining the prefix minimums. That's the idea. It's kind of annoying, slightly. This one's even more fun. I'm not actually sure what's the smooth way to do this, because what I did was by no means smooth. So you're given a grid of 2 by n with 2 rows and n columns. You have at most 2 times 10 to the 5th blocked cells. All the other cells are free. And you basically want to ask, can you tile the board with 2 by 1 dominoes? That's the question. And the size of the board is at most 10 to the 9th. So the first thing to deal with is the size of the board, because if we didn't have the size of the board constraint, we can do some sort of like broken profile DP, where like DP of I and then column basically represents, no, it's like, we have dp of I in mask stating that we can get to the ith row, or we can get to, for example, the third column, having like a certain mask of the cells filled in or not. So for example, this bit in the mask would be set to 1 if the first thing is filled, and if not, it would be 0, and the same thing for the bottom one. And then we can do some transitions for putting down tiles using that. Like we either put down nothing, put down the horizontal one, put the first vertical one down, the second vertical one down, or both of them. So we have 5 transitions. And of course, putting nothing down only works if we already have block cells, but that's a possibility. So the main observation is like because there are so few because there aren't that many block cells relative to the grid size. Of course, 2 times 10 to the 5th is a lot, but still. Like say we have 2 cells that are like a million apart. The intuition is that like we should be able to treat them almost the same as when they're close together, because we get a lot of freedom in this range. We can basically do whatever we want. And one thing we can do is simply like place down the 2x2 cells and like place down a lot of them. So like we can place these down here and then place these down here and then do this like 500,000 times, for example. And in general, it's fine to do this, because if we need to do something else, we can do it at the very beginning and also at the end, and then just fill in the rest with these 2x2 cells. So like up to a certain point, if we bring these 2 cells too closer together, like 2 units closer together, then it's not going to hurt. And I think the minimum distance where it does make a difference is like less than 4. Because if you have like 4, for example, or like let's say less than or equal to 4, because if you have like 5, for example, then like just imagine the possibilities. Whatever you do with the ends, basically they're only going to reach like at most 1 into this and at most 1 into this one. So you have this gap of 3 where you're basically like free to do whatever you want independent of the ends. And so therefore you can like reduce it by 2. And I'm not sure about 4, so what I did was I just didn't change it if they were 4 apart. Just to be safe, I made it so it was at least 5. But basically the idea is you can bring the cells closer together and closer together and closer together up to a distance of, let's say at least 4, or let's say at most 4 apart. So now each cell only contributes like O of 4, like each cell only contributes like at most 4 units to the grid. And instead of having a grid of size 10 to the 9th, now we have a grid of size like 4 times m, where m is the number of block cells. So after compressing this grid and also compressing the endpoints, because we can also compress the endpoints in the same way, like we can just stick 2 block cells in the end here and then the end here, and then we can treat it like normal or something, then now we're just happy. It's peaceful because we only have 4 times m grid cells, which is like a size of 10 to, like less than 10 to the 6th or something. So it's not that big a deal. Maybe exactly 10 to the 6th or something like that. But now we can basically set up this DP with the compressed grid. So these transitions are fun. Let me show you how to do this DP. So basically we're going to work with this 4x4 grid. We're going to use this column to transition into this one. So basically we're going to place tiles so that their right endpoint is on this column, is on the right column. And so possibly some of these are blocked out. This depends on the DP state, of which we have 4 of. So like state 0 would represent both cells being empty. State 1, for example, would represent the top cell being blocked. State 2 would represent the bottom cell being blocked, and then state 3 would represent both of them being blocked. So like, for example, like this. Right. Now, say we want to do the transition of putting the horizontal one here. Now, because we're not... Now, by putting this here, we're basically saying we're not going to put any more dominoes to the left of this. Because if we were, then we would have handled it already in this case. So that means that this whole side of the grid has to be fully resolved. And that means that we can only do this transition if we're able to achieve state 3 in the previous one. Because otherwise, like, we have some empty cell here, and it's not possible to do this horizontal one. So case 1 is horizontal. And it only works if A, neither of these cells are blocked, and B, we have DP3. So case 2 is we can do nothing. So again, if we leave some cells blank here, and we leave some cells blank here, then we're basically saying the next domino we're going to put is going to be on this column, which means that we'll never be able to reach this blank cell over here. So we can only do nothing if both of these cells are already filled in, which again means we need to have state 3. And then the new state we transition to is entirely dependent on whether these cells are blocked or not. And we can basically figure out the new state from which of these cells are blocked. Because it just becomes, the new state becomes exactly the blocked cells in the column. So we can put, the next transition is we can put the top vertical one down. Number 1. Or vertical top. So we put this one down. This only works if, and that means we're putting nothing here. So this only works if A, this isn't blocked, because obviously we wouldn't be able to put the bar down otherwise. B, that we have access to DP of state 2. That is, we are able to fill this in somehow. Because if we didn't fill this in... okay. My door just opened by itself for some reason, so I'm going to close that really quick. My house is messed up. There's like some hinge broken and stuff. It's weird. So if we haven't filled this in before, then we're never going to be able to reach it with a cell that starts over here. So we need to have filled this one in. So if we take state 0, this won't be filled in, so it's invalid. If we take state 1, both this will be filled in and this won't, so it's invalid. State 2 will work, and state 3 won't work because this will be filled in. So state 2 is the only transition where we can put the vertical top down. And then we need to check if this cell is blocked, and then our new state depends on if this cell is blocked or not. If it's blocked, we get state 3, otherwise we get state 1. So then we can do vertical on the bottom, and it's basically the exact same transition, so I will not go over that. And then we can do 2 verticals, which means we're going to do this and this. And this one's probably the clearest. It only works if A, both of these cells are not blocked, and B, we can achieve DP of 0 in the previous column. So those are basically the transitions, and then we can figure out which DP values are possible for this column. And then we just continue on until we get to the end. Now what I did for implementation tricks is I sort of virtually extended the grid like 5 beyond n, so you can go up to like n plus 5 or something. And of course, refactor n to be the size of the compressed grid, not the full grid. And then from that, the answer is basically DP of, is it possible to get DP of n in 3? Because we need the full grid to be filled in, meaning we need to end on a full state. So that's basically it. N plus 5 is just a trick so you can like not worry about runtime errors, which I had anyway, actually. Another thing to note that I didn't realize for some reason, the order of the cells are not necessarily sorted by column. So be careful with that. You first sort the values by column so that you can do the compression without it being annoying. Just be careful in general. Then this is problem G, and basically the way it works is you have a directed graph. So let's, for example, do this. You have 1, 2, 5, 3, 6, and this. My mouse sensitivity is going crazy. And we have a bunch of edges. It's like this, right? Yeah. Okay. Now the first thing we do is we compute. So this is the root cell, or the root node. And then we compute for each cell the shortest path from the root to that node. So this is something we can do easily with your favorite shortest path algorithm, something like BFS, because the graph is unweighted, or Dijkstra would work. I just basically pasted in my Dijkstra template. Also, I just realized I forgot to go over my code for F, which is probably a good idea. So my code for F basically just I have a function for getting the distance, and then you do the compression just by compressing any huge distance to a number that's either 3 or 4, depending on the parity, and then just do the transitions depending on what matters. It's relatively simple given my description of it. Okay, so again, I'm going to timestamp this out now. For G, you have a directed graph, and the first thing you do is, you know the root node of the origin. They call it the capital. And basically, you compute the shortest path from the capital to every other node. I think it's connected. Do they say that it's connected? Yeah, it's guaranteed that there's a path from the capital studies. Okay. So yeah, this is the idea, that you can always do stuff like this. And you compute the shortest path from the capital to every other cell, city, whatever. And now we basically ask, for each node, we can only move down edges that go from a green value to a higher green value. That is, it gets farther. The shortest distance from this value to the capital is increasing, strictly increasing. Basically, we can once we compute these distances, we can basically treat these like array values, because we don't really care about the distance part anymore. It's just we have array values, so it's kind of slightly pointless to have this whole thing, I'm pretty sure, and that it doesn't really matter. Although maybe there is some way to do it smoother than the way I did it, depending on this description. But I don't really know. That is interesting, actually. Yeah, okay. Well, anyway. Maybe there's a smarter way to do this that actually uses the facts of the problem, but I did not do that. I just treated this like an arbitrary array and then may have overkilled it. So that's fine. Basically what you can do is you can move from some node to some other node if its array value is larger, strictly larger. And you basically want to figure out for each node as a starting position, what's the largest or what's the smallest array value you can get to. Now, there's another twist in that exactly once Yeah, I definitely overcomplicated this. Okay, you know what? Whatever. In exactly once, you can move from an edge with a greater array value to an edge with a lower array value. So basically, like for example, the answer for this node would be well, you can go directly back up to 0 because you can use the one edge, so that works. Actually, no, sorry. And to do that, you also need there to be no, that's wrong. You need there to be an edge from, like, the edge has to exist. The edge has to exist, which means, like, it has to be directed and the edge has to exist. And exactly once you can move from a higher value to a lower value, or a lower equal value. So if we consider the new graph, where there's an edge only if we can do the valid move, then we're basically asking, over all reachable nodes, like, where's the best we can get? Assuming that, again, we can do exactly one move upwards. So this is something I did not realize in my own code because I didn't really do much thinking about this. But firstly, what's our optimal path going to look like? So if we start, for example, here, then maybe we go down some. Like, we always go down values. And then yeah, we always go down, we always like increase in array values up until the very end where we may decrease by 1 because we want to minimize it. So once we like do the move where we go up and then we like, once we do our singular move where we decrease the array value, there's no reason to ever make another move because every other value is always going to be higher, like by the definition of the problem. So our path is basically going to be, we move down until we eventually move like to greater array values maybe, and then eventually our final move will consist of going up to a lower array value, and that'll be it. So now, like, for each node, we can basically say, what if this node's the ending node before we do our special move? Then we can like compute a new value that is sort of the best we can get doing the special new move from this node, which is essentially for each edge going out from here, what's the minimum array value? Because the minimum will take into account that we can also go down array values and do our special move. So for example, here, we can't go anywhere from here, so this would be something like infinity. Here, we can go down to the 1, and this would be our special move, so we can do 1. Here, the best we can do is 1. We can go to 2, but we can also go to 1 using our special move. Here, the best we can do is 0. This was what it was, right? Okay, yeah. Here, the best we can do is 0 because we can go up, and here, we're obviously at 0, so there's nothing better we can do. So now, we're basically asking for each node, of all the nodes you can reach by not doing a special move, what's the best orange value you can get? And so we create this sort of new like imposed graph, which sort of just says like, we only have an edge if the array value is increasing. So for example, we have this edge, we have this edge from 0 to 1, we have this edge from 1 to 2, we have this edge, no, we don't have that edge, we only have this edge. And then now we're asking the same question for each node, what's the largest orange value of the reachable nodes from it? Actually, this would be 2, not infinity, because we can still get 2, no matter what. Yeah, I don't know why I drew an infinity there. It doesn't really make sense. So this is 0. This is 0. Yeah. The other thing to note about this graph is that it's a directed acyclic graph, or a DAG, because we only have an edge from some value to some other value greater than it, which means that there exists a topological sort because of the fact that we like only have edges where values are less than other values. So then with that, we can do like the standard like DAG DP, where we iterate in the reverse order of the topological sort, and then say that, like, for example, the best for this node is the best either of this node or of the nodes it can go to. And you can do this either recursively or iteratively. It's probably easier to do it recursively, because then it's just like you can work out the topological sort. It'll work it out for itself. If you do it iteratively, you can go like in reverse order of the topo sort, which is what I ended up doing. And then and then you can do the normal sort of DP to figure out the smallest reachable orange value. And that basically does it. What I did was much less smooth. I didn't even realize that, like, there's no reason to ever take another edge after you do the special move. So I basically like did the initial DP where you assume that you don't use the special move and then do it like on the green values, and then finally I computed the orange values with the newly updated green values after doing like one iteration of the DP, and then I did it again even though the whole thing was like the whole first thing was completely redundant, but I did it anyway. So yeah, that was fun. But it ends up being equivalent because, like, the first move is totally useless, but it doesn't harm anything. Because, like, the second move will cover everything that the first move does. So, like, the first move is just a subset of what the second move can achieve. So it's like it's not harmful. So I did the DP iteratively, which is not smart, doing like the reverse of the topological sort, and then I did it once, and then I computed the orange values basically, which is again the minimum immediately reachable green value, or the distance values, or the array values, whatever you want to call them. And immediately reachable just means like adjacent and reachable. And I computed the orange values, and I did the reverse topo sort again, and then that's how I got the answer. Used a lot of things. It was fun. It was fun implementation. Let's see. Did I get top 200 at least? Have I been hacked? Maybe I have been hacked. Okay, anyway, yeah, this was not good. This was very not good. I don't know why. This was just dumb. Should not have messed up so much on E. I had like dumb mistakes like not accounting for equal values, or at the same time. My final mistake was forgetting to do the swap, even though I did this whole thing to prove it. So it would just be like totally wrong. And for F, I had some runtime errors because I didn't realize that the things weren't sorted. So that crashed it. And then G just took a while to implement because I overcomplicated it. So yeah, these were fun problems. Maybe there's a way to like not be dumb for the whole thing, but maybe not. Maybe you can actually use the fact that these are shortest distances. Like maybe that has a role to play. But I'm not really sure. For this one, it's just sort of doing it. Like doing the compression, bashing things out. And yeah, I don't have much more to say. I don't know how to feel about the problems. Because I overcomplicated them, I feel like my opinion is a bit biased, so yeah, I'll leave it at that. Alright, goodbye all.